So now this session, now this webinar has been live streamed on YouTube, and let's wait for a few minutes for people to join. Then you'll be officially start in roughly 3 minutes. So cool. I think it's about time to start. And yeah, first of all, everyone, welcome to the Flower Monthly this in April. Sorry, it's yeah, it's in April. Sorry, it's in. And thank you for joining us today. And also great to have our speakers talking about fair learning and agentic AI. And also, it's great to and also thank you guys for joining us on Zoom, on YouTube, and also on other platforms. And for this monthly, the agenda is very simple. And let me quickly walk you guys through. The first of all is, of course, the welcome message, the agenda, and also briefly after this page, I'll give a short flower update. It's mainly about the news. And after this brief session, we'll have our first speaker, uh, our first speaker talking about multi-agent framework in federated setup, and followed by another talk about efficient federated learning on edge. And then lastly will be me on the flower simulations. And yeah, the for on the flower update, yes, the biggest event, the biggest update we have is actually uh, our upcoming event, the Flower AI Summit this year, the Flower AI Summit 2026, happening in less than 2 weeks. And it's focused on open source and federated and agentic AI. And if you are interested, you can find more details and apply through the link on the website. Also, I posted here. And it will be hosted in King's House. It's really a great venue for both talks and networking. It's a nice place for for bringing everyone together and in a more interactive settings. And also we have some photos from the last year's summit. We have talks, demos, poster sessions, discussions, and a lot of community interactions. We also have a pretty good buffet there. And it's not just presentations, it's also a great chance to connect with others working in federated learning or agentic AI. And also, this year we'll have a lot of amazing speakers coming from big techs and top universities, and also from both academia and industry. And if you are working in space or just interested in the related topics, and definitely worth attending. And then that's all the updates. Let's move on to our first talk. We are happy to have Mohammed Ripon from Islamic University, Bangladesh. He'll be talking about the AgentFedNoise. It's a multi-agent framework for adaptive noise control in privacy preserving federated learning. Please join me in welcoming him. And I'll hand over to Mohammed.
Thank you for having me here.
Would you like to share your screen? Yeah, I think yeah, I can see your screen clear.
Where maybe I'm facing some problem.
Is a slide? Can you share your slide, or it's not responding?
Okay, sorry for the disturbance.
No worries. Yeah, it's working pretty good this time.
Again, thank you for having me here. Today I am representing my project as AgentFedNoise. This is a multi-agent framework for adaptive zero-sum noise controlling privacy preserving federated learning concept. So let me uh, introduce myself. I am MD Ripon, Research Assistant, Cybersecurity, IC Innovation Lab, Department of ICT, Islamic University, Bangladesh. Alongside, this project is supervised by Professor Dr. Vikas Chandra Singh, Assistant Professor, California State University, Fresno. Okay, these are the outlines of my today's presentation. So at first, I will explain how the zero-sum noise is how the zero-sum noise is work in our project. Then I will explain the multi-agent controller concept. Okay, in this introduction slide, I picked two terms, conventional machine learning and federated learning. As you know, in conventional machine learning, raw data from different sources sent to a single server and then aggregate centrally. On the other hand, in federated learning, only model updates sent to the central server. Hence, it enhances privacy as raw data never leaves devices. Besides, it has some challenges like model updates may leak information through several attacks. Okay, this is a federated learning scenario, which I have already mentioned. Uh, though the federated learning itself secure system, but there are various attacks already have been done in federated learning. One of these is inference attack. In inference attacks, attackers analyze shared model updates to infer sensitive information about participants' local data. Another question is who will compromise or with the attackers? So if we go back to the our previous slides, that we can see two layer. One is the local devices, other is the aggregator. So in our project, we consider the local devices are safe and the aggregator may be biased or compromised with the attacker. So our job is to protect the weight or updates uh, from the local devices. Okay. So in this case, there are several work have been already done, like members inference, federated property or level inference, model inference on it. So this is our proposed model. Then how we protect the weight updates or weight updates from the local devices. So we have introduced a tossing mechanism for randomize. Actually, we used here a local differential privacy with a randomized mechanism. The noise will add with the updates with a randomized mechanism that there is a tossing mechanism we can see, and then the lucky updates from the local devices will add noise, then add to the weight updates of the local devices, then go to the distributed loader, and we are applying a mathematical approach that why the aggregator when the aggregator aggregate the updates from all the local devices, they are cancel out each other. Okay, here is the mathematical explanation of our proposed model. Here, I already mentioned, as I already mentioned, there is a tossing system. We introduce here Bernoulli marks for tossing. This is a binary tossing. Okay, then according to the Bernoulli marks, then Laplace noise will be generated for the selected coordinates. Then here is a simple mathematical explanation how the noise will cancel during the aggregation. Okay, this is the experiment setup. Here we can see two table, one federated testbed and privacy configuration, and other is dataset characteristics as a function of number of clients. The dataset we consider during our experiment. And this is the parameters of privacy configuration. Here we done our experiment in four setup. One with the 3 clients, and then 5 clients, and then 7 clients, and then 10 clients. All the setup will introduce 10 rounds. Okay. Here, one more thing I have to mention that the privacy budget, which will help us in Laplace noise, to produce noise. Okay, this is fixed. This is fixed here. 5. Okay, brother, when he explained the multi-agent controller, then the privacy budget uh, there will control by the agents. Okay, and here we use two server. One is our default server, Federated, another is custom server for our further experiment. So, okay, in the result and discussion, we will see if our zero sum noise mechanism is work. So for this, we store mean of noisy updates and mean of original updates before sending the aggregator into different JSON file and plotted them in in a group, then we'll see they are overlapping. That means the noise is cancelling, and our mechanism is work. Okay, so we have done this experiment with the four setup for 3 clients, 5 clients, 7 clients, and 10 clients. So all the time we got the same result. Okay, we also experiment that mean of original update versus mean of aggregated updates. That means we also store the mean of original updates and the mean of the aggregated updates. The mean of the aggregated updates we found after the aggregate or aggregate the updates. Okay, so this will also overlapping in our experiment. So we can say that the noise perfectly cancel out during the aggregation in our mechanism. Okay, so finally, this is the accuracy comparison. We can see accuracy over rounds, no noise. Left and right is accuracy over rounds during the distributed LVP. So I have one thing. I have one thing. I should one thing mention that the noise is distributed. That means the noise is generated in one location, then distribute it through the local devices. Okay, the accuracy you can see the every setup they are identical, so that almost identical, and accuracy are almost same. So we can see that our some LDP is working here. Okay, now we are moving from a static privacy preserving federated learning to a dynamic privacy preserving federated learning. Now, this is the multi-agent controller. The multi-agent controller decides epsilon per client. As I mentioned in the previous slide, that the epsilon or the privacy budget was fixed. So instead of one static epsilon, the server computes a privacy budget for each client using both privacy and utility signals. Okay, for that, we are introducing free agent. One is privacy agent, other is utility agent, and the last one is coordinate agent. Okay, the first one is privacy agent. Here is a sample of a snapshot of my project, that how the privacy agent work. This agent asks, does this client need stronger privacy this round? Actually, this agent pushes the system toward more protection when the client update looks more sensitive. It will smaller the epsilon, and then it will smaller the epsilon, then the privacy is then the more noise is more and the privacy is high. Okay, it uses the update norms and sensitivity score. Here, a simple static example how it behaves. Okay, now the utility agent. Okay, this agent asks, does this client need better performance? Okay, this agent this agent will work with the performance, with the accuracy of the model. Okay, it uses three parameter loss, accuracy, and global trend. When it sees that loss is high or accuracy is low, it's reduce the noise by increasing the silence. Okay, it looks about it's concerned about the performance of the model. Okay, here static example how it behaves. Now the last one is coordination agent. Okay, this agent asks, how do we balance privacy and utility for each client? Okay, in our previous slide, so we see that privacy agent saw that privacy agents wants smaller silent, and utility agent wants larger epsilon or privacy budget. But the coordinator finds the right balance. It ensures either privacy nor utility dominates completely. Okay, that's all about the concept of my multi-agent controller. So hence, this is adaptive noise control concept at all. So we have some future plan that we will go our noise generation technique into a blockchain for more robustness, and we will simulate some attack to test our test our project robustness. Okay, this is references of my slides. Feel free to ask question. Thank you. Thank you for listening.
Well, it's a great talk. Thank you for sharing. And let me check if we have any questions from our platforms. Well, actually, on my side, I do have one question. Out of curiosity, when we say zero-sum noise, is it mathematically guaranteed to be zero, or is a probabilistic guarantee?
It's mathematically guaranteed that the noise will cancel out
I see. So,
in the
does this noise generation, the cost of generating this noise scale with more clients? For example, if I wanted to have 1,000 clients, will the
uh,
cost of the noise generation also increase?
uh, yeah. Uh, Basically, we done our experiment with the highest client of 10 clients. So this will work. We are working on it
See? Cool.
because the mathematical formula built in a way that if you if you increase the number of clients, it doesn't matters, or it makes this no differences.
I see. But will it be more compute expensive?
Yeah.
I see. Yeah, that would make sense. I don't currently see any questions. So I think we can moving on to our next speaker. Uh, would you mind me stop sharing your screen? Yeah. And yeah, the next speaker is uh, Leming from UCL and also the Hong Kong Polytechnic University. He'll be talking about efficient fairy learning on edge devices. And Leming, the stage is yours.
Okay, let me share my screen. Okay, so you can see the screen, right?
Yeah.
Okay. Thank you so much, and thank you everyone for the invitation. And yeah, so hello everyone. My name is Leming Shen, and I am currently a PhD student from the Hong Kong Polytechnic University, and I am also a visiting student at UCL. And today I would like to share our recent research towards efficient federated learning on Edge. So federated learning has been a popular research topic for several years, and it enables distributed mobile devices to collaboratively train a global model without transmitting their private data. So specifically, the server will first create a global model and transmit it to federated clients. And in each communication round, the clients will train local models with their private data and only upload the model parameters to a central server. And with the received parameters, the server will orchestrate model aggregation to generate a new global model and for the next communication round. So, but however, in real world scenarios, we know that mobile devices typically have diverse system resources. For example, a laptop has larger memory capacity and has more computation power than a mobile phone. So therefore, it can support models with more parameters, while mobile phones or wearables cannot support large models. So if we simply assigning the smallest affordable model to all clients, it will result in suboptimal performance and also resource underutilization. However, the challenge here is how can we generate heterogeneous submodels to fit each device's resource budgets? One of the existing solutions is parameter sharing, where the clients share different parts of the model parameters. So, for example, here we can see that these smaller models share the upper right corner of the large model. But however, we find that this kind of parameter sharing methods will lead to imbalanced training with degraded performance. So let's take this figure for an example. We can see that the parameters are aggregated only from clients that have the parameters. So in the blue unshared part, only clients in laptop will participate in the training process. And therefore, this part in the aggregated global model will miss information from other clients. And we conduct a preliminary study, and we can see that smaller models will achieve better performance as their parameters are shared by all the other clients. And also, we can see that the aggregated global model exhibits instability and even performs worse. And another existing solution is model pruning, which includes channel level and the filter level pruning. In channel level pruning, some input channels of the model parameters are removed. So the corresponding channels of the input data are also excluded from the training process. And in filter level pruning, some output channels of the model parameters are removed. So the number of generated feature maps will also reduce. However, we find that these kind of pruning-based methods will cause information loss because we have less input data and also we generate less output features. And this also leads to performance degradation. And in addition, the pruning process is usually performed on the client, which may also lead to extra computation overhead. So the pruning structure will be transmitted over the network and increase the communication overhead. So we also conduct experiments and we measure the mutual information between the parameters before and after pruning. And the higher mutual information value we have, the more information can be preserved from the large model after pruning. So we can see that neither of the two pruning methods can preserve parameter information because they both achieve a low mutual information value. So this indicates significant information loss after pruning. So ideally, if we want to design a submodel generation method, we should minimize the information loss after model compression, and also we should retain the model's performance. And last but not least, we should not impose any extra overhead on those mobile clients. And our answer to this requirement is convolution. So we know that convolution can extract effective features from input images. And we claim that we can also use convolution to extract crucial parameter information from the large global model. And the model parameters after convolution will have smaller sizes with more parameter information preserved from the global model. So to better understand how our convolutional compression method works, let's take a simple CNN, for example. Now let's consider this kind of CNN networks. The first convolutional layer of the global model will generate 16 feature maps, and the second layer of the global model will generate 32 feature maps. And now suppose we want a submodel with a shrinkage ratio of 0.75. So after compression, the first layer of the compressed model should generate 12 feature maps, which is 16 times 0.75. And also correspondingly, the second layer should generate 24 feature maps. Okay, so by comparing the generated feature maps, we can observe that the first two feature maps from the submodel pay more attention to the deer's body and ears, and the third feature map of the submodel can be regarded as a fusion of the last two feature maps from the large model because it focuses on both the deer's body and the head. And also, we measure the model accuracy and the mutual information value. We can see that they both achieve very high scores, and which is comparable with the pre-trained large model. And so this indicates that our convolutional compression method can effectively preserve the parameter information embedded in the large global model. So how do we leverage convolution to implement such model compression? We need to first configure the convolution parameters so that the size of the compressed model matches the corresponding shrinkage ratio. So again, let's take a network layer as an example. This network layer of the large global model has its parameter matrix has a shape of 32 multiplies 16. And if we feed it into a convolution layer with 9 multiplies 5 kernel, we can get a small parameter metric, which is 24 times 12. And that is the parameter of the submodel. So as long as we can vary the configurations of these convolution compression layers, we can generate submodels of any size we want. And to retain the performance of the compressed model, we need to fine-tune the convolution parameters. So therefore, we propose a learning on model paradigm. So let's again consider this computational graph. After generating the small model via convolutional compression, we feed a part of the data into the small model to generate outputs. And then we calculate the loss based on the label. And finally, we backpropagate the loss to the convolution parameters, not the global model, also not the small model. We backpropagate the loss to the convolution layers, and we iteratively update it for several epochs until the compressed small model can achieve similar performance to the global model. So such a learning on model method fundamentally differs from the traditional learning on data method. In the traditional learning on data paradigm, we take raw data as input and train a model to extract features from the data. But in our learning on model paradigm, we take model parameters as input and use compression layers to generate submodel parameters. And now I will present the overall workflow of our system, which we named it as FedCom. So specifically, the central server first initializes a large global model, and then each heterogeneous client will first perform resource profiling and estimate an appropriate shrinkage ratio and send it to the server. And based on the shrinkage ratio, the server will configure different convolution parameters to compress the large global model into submodels with different sizes. And the submodels will be transmitted to the clients, and clients will perform several epochs of local training using their private data sets. And after local training, the updated submodels will be uploaded to the server, and corresponding to the convolutional compression process, the server will apply transposed convolutional dilation on the submodels, which will expand the submodels and expand them into a large global model with a unified size. And lastly, the server will assign different weight vectors to the dilated models to perform aggregation and update the global model for the next round. And we can see that the model compression, dilation, and also the aggregation process are entirely performed on the powerful server, and the clients only need to perform local training, just like traditional FL systems. And here is the experiment setup of our system FedConf, and we implement FedConf with multiple heterogeneous edge devices deployed in our lab, and we use Flower as the FL framework, and we use PyTorch as the neural network framework, and we modify its package to enable the backpropagation to the convolution parameters. And we choose two tasks, including image classification and human activity recognition with different data sets. And we also compare the performance of FedConf with 9 baselines from including knowledge distillation, parameter sharing, and model pruning. And to evaluate the training performance, we measure the inference accuracy of the global model and client models. And we also measure the total communication cost. And to evaluate the runtime performance, we measure the memory footprint and also the wall clock execution time of each client. And these two figures illustrate the global model accuracy and the client model accuracy. And we can see that FedConf achieves an average improvement of 20%, 13%, and 10% compared with pruning-based methods and parameter sharing-based methods and other baselines. And these results demonstrates the superior generalization and also personalization performance of FedConf. And this figure shows the inference accuracy with different heterogeneous data distributions. And we can see that FedConf is more robust to heterogeneous data distribution. And the performance gain of FedConf becomes more efficient when the data becomes more heterogeneous. And although FedConf underperforms a baseline called FedMD when the data is extremely heterogeneous, but FedConf can be further enhanced by some personalization methods, such as we can add in some task-specific layers at the client side. And moreover, FedConf also consumes less CPU and GPU memory with less client-side workload time. And lastly, FedConf saves communication costs compared with other baselines. So to conclude this work, we propose FedConf, which is a client-friendly federated learning framework for heterogeneous clients, which aims to minimize the system overhead on resource-constrained mobile devices. And FedConf features 3 key technical modules, as we mentioned before, including convolutional compression, transpose convolutional dilation, and also the weighted average aggregation. And last but not least, we believe that our proposed learning on model paradigm is worthy of further exploration towards efficient FL. And the source code of this project is also available at GitHub. And this paper is published in Mobices 2024, and I want to express my sincere gratitude to all my amazing collaborators. Okay, so before ending this talk, I would like to share some of my thoughts of FL in the future. So now let's envision a multi-robot collaboration scenario where each robot has a general embodied AI model or agent. And in such cases, we may face several problems. The first one is the environment heterogeneity. We know that mobile robots often operate in expansive environments, and they observe their surroundings from different angles. So if we simply use pre-trained SLAM models or multimodal LMs for environmental comprehension, we may face inadequate generalization abilities to heterogeneous environments. And the second is the task and action heterogeneity. In other words, we say that the heterogeneous environments will further amplify the variability of the decision-making process during task decomposition and also action execution for robotic manipulation. So for example, if we want to grab an apple for the user, the decomposed tasks can be moved to the table and find the apple and grab the apple in one environment. But in another environment, the decomposed task can be moved to the fridge, open the fridge, and find the apple and grab the apple. So these are the task heterogeneity. And the third challenge is collecting real-world robotic data is both labor-intensive and time-consuming, and also the quality of the data is questionable. And last but not least, existing vision language action models, VLA models, they also exhibit extremely limited generalizability to different robotic configurations and also environments. So to tackle these challenges, we envision that the future of embodied AI should also be federated. And this is an illustration figure of federated embodied AI. So we consider three levels of information to be shared through federated learning. So first, we claim that federated agents can collaboratively enhance their perception and understanding of the physical world by sharing some environmental information, such as semantic maps and also spatial relationships. And the second, to support generalizable task planning, we believe that federated embodied agents can also share some abstract representations of how complex instructions are broken down into manageable steps. And by exchanging these task templates, agents can contribute their experience in translating high-level goals into actionable plans across different environments. And last but not least, the federated embodied agents can also improve their capability to interact with the physical world by sharing some manipulation policies, which can capture how specific actions are performed and evaluated in different contexts. And each agent contributes high-level descriptions of successful behaviors, such as how to grab an object or navigate to a cluttered space, and along with the conditions that define the success or failure. So we believe that these policies are then can be organized and generalized into to create shared guidelines that reflect best practices across environments. And by learning from each agent's experiences, those federated agents can develop more robust and adaptive manipulation strategies that transfer across heterogeneous real-world environments. And yeah, and that's all for my talk. And thanks everyone for listening. And I'm happy to take any questions.
Well, thank you so much for the insightful talk. And I'll check our Slack channels and YouTubes. Cool. On my side, actually, I think your vision on the federated agent and sounds very intriguing. And apart from that, also I'd say the convolution. I think the convolution layer for compressing the model is a very interesting direction because feels like it's a mixture of architectural compression and knowledge distillation. So I think it's a quite interesting direction, and obviously it successfully downgrade the model without significantly reducing the performance. And yeah, also not normal knowledge distillation seems to just use the output and logics, but here also in some sense, learning the pathway of thinking, the reasoning pathway from the global model. Yeah, it sounds very interesting. Um, quick question. How would you design these convolutional operations? Like how you choose the parameters when downgrading?
Okay, let me see if I prepare some backup slides. Okay, so actually, given the size of a large model parameter and the size of the target submodel parameter, actually we can have many kinds of convolution configurations as long as we follow the mathematical calculation, we can also generate the submodel. So in our experiments, we also try different kernel size and the stride length of the convolution parameter. And we find, so based on the experiment result, we find that we choose the optimal one. Yeah. So here uh, uh, with more red color, the higher the accuracy of the compressed model achieves. So we just build like this kind of map, and we choose the optimal parameter configuration. Yeah,
Makes total sense to me. Yeah,
yeah.
cool. Yeah, thanks so much for the explanation. And let me double check. Any questions? I don't think I see any questions. So yeah, no, I think that's yeah,
Okay,
yeah,
thank you.
cool. Thank you so much. And yeah, so today I think well, thanks again for the insightful presentations from both of you. And I think now it's I'll take the final bit of this session and I'll talking about giving memory to flower simulations. It will be a very lightning talk, around 5 minutes. It's actually about a new feature we offer in the latest flower version. Let me show my screen. Cool. So with flower, yeah, we know that many of us are using simulations. So how to run simulations? Today is very straightforward. Once you have a Flower app, just go to the app directory and then execute Flower run. Then you probably get something similar to this. Like go to my awesome app directory and then just do Flower run, and the dot means it's just the current directory is where my app is, and I'll run it. It's very straightforward, and also it's very simple to run it without having to configure different things. But also there's one small issue with that. So Flower Run is a short-lived process. So how can we really find these simulation runs? Like how can we track? How can we manage? How can we revisit all the simulation runs we submitted after the experiment is completed? Of course, we can definitely create a log file and then redirect the output from the Flower run to the file. And now Flower is offering an alternative here. So it's exactly the same, but go to the app directory, then do Flower run with stream. Now, this is the thing that comes slightly different. This actually means we are streaming the log from a different process. What happens under the hood is that now, instead of before, Flower run will just spawn a process running the entire simulation. But now, Flower run will just submit a request to a local superlink. If you don't know what's a superlink, it's the Flower server, and this Flower server can also manage simulation runs. And that means basically the Flower run will just become a very lightweight control signal telling the local the local superlink, more like a simulation service that I want to start a run. And then it will get started. Then what's a good part about this? Well, it's very straightforward, and I think it will be way more easy for me to just share my terminal. So currently I have a terminal and I'm in a quick start numpy example. And obviously I can do flower run dot with stream, meaning that I need to stream my logs from the process that actually executing the simulation. And you'll find it will see exactly the same thing. Nothing seems to change. That's good actually. And what actually we offer here is that with a local superlink, it offers, for example, flower list. You'll be able to find all your submitted runs before, and also you can easily find like the run ID, the status of the run, and how long they take, and the status of them, like when the status changed. Also, this is a run I just submitted a few minutes ago. You can also use flower log to retrieve the logs again. You never lost your run. You never lost the history of these logs. Like, for example, I copied another run ID here, and I can also find it. Although it's the same, of course, because I just resubmit the same run again. Similarly, you can also track things in more detail by passing flower list, but I just want to check a very specific run, and then we can see more details, including when this run gets submitted, when it's started, when it's running, and when it's finished. And Flow now will help you to track all the runs, and you can easily like testing with different settings. Like I want to change this number of similar server rounds, number of server rounds to, for example, I want to have uh, I want to have 1,000 rounds, 10,000 rounds, and it will start streaming. And when you do Control C, you exit the log streaming, and then maybe go grab a coffee, go for a lunch, and you'll see, oh, 1,000 round caused my map to slow down a little bit. I should stop it. Yeah, you can use flower stop to stop any existing runs. And all these things will be logged, will also be tracked by the local superlink, and then you can retrieve the endtime and all the relevant information. You can find them in the flow directory. By default, is in the .flw flower home directory, and you can also find the logs there. And for more information, you can just visit our website. And yeah, that's the local superlink I'd like to share. Let me stop sharing. Yeah, sure. Cool. Cool. Going back to my Mac. I shouldn't run 1,000 rounds. It's so slow now. Oh, 10,000 rounds. Okay, moving on to different screen. Um, Uh, cool. And that's the flower monthly for in April. And the next time is and our next monthly will be at the 6th of May in the same time, the 6 p.m. UTC time. You can find our website on flower.ai and see the flower monthly page. Also, if you have any feedbacks, we can go to the flower-monthly channel on our Slack channel. And you can join our Slack workspace here via this link. And also, you can track all our flower events also on the flower.ai website. And yeah, that's the entire flower monthly. Thank you everyone for joining, and also thank you both for the great presentations. And hopefully we can meet you guys very soon, probably in the flower summit. And yeah, that's everything. Thank you. Thanks again, and see you next time.
Okay, thank you. See you.
Take
Thank you.
care.
See you.
Have a good rest of the day. I will now end this webinar.